On our third formative assessment, we were asked again to graph a polynomial. And here is a polynomial equation. It's in factored form, so that actually makes it really easy to graph. Another thing that makes it easy is that I've given you a bunch of hints about things that you should include in your sketch. I'm going to do these a little bit out of order, maybe, but first I want to go with the very first hint. I want to find the roots of this polynomial and then label them with their x coordinates. And the roots are the values of x that cause the function to be 0. And using the zero product property, we can see that if any one of these factors is equal to 0, then the entire right-hand side is equal to 0, which makes our function equal to 0. And you should use, just by inspection, notice that x equal to 1, x equal to 4, and x equal to -3 are the values that cause this function to be equal to 0. So I'm going to locate those. Here's x equal to -3. Here's x equal to 1. And here is x equal to 4. So I don't need to scale my axis perfectly or anything. It's a sketch. Okay. The next thing I want to think about is let's just talk a little bit about the y-intercept. In order to find the y-intercept of any function, you just need to plug in 0 for x. And the reason is because the y-intercept is the point somewhere on this y-axis where the graph crosses the y-axis. And anywhere on this y-axis, the value of x is equal to 0. So if I just put 0 into my function for x, I get -1 to the third power times -4 times 3 squared. And just using my order of operations, I'm going to do the exponents first. -1 to the third power, that's -1. The -4 is just to the first power, so it's just copying that over as I simplify. And 3 to the second power is 9. So -1 times -4 times 9 is a positive 36, and that's my y-intercept. Before I try to locate that point on my y-axis and label it, instead what I'm going to do is just acknowledge that on this interval between these two roots, my function is positive because it's going to have to go through positive 36 up here. And I can pick an x value on any other interval, like down here, or in between these two roots, 1 and 4, or above the 4. I could pick any value in there just to test and see whether the graph is going to be negative, like on the bottom half of the graph, or if it's going to be positive, like it is on this interval. But I can also use the multiplicity of these roots to determine that. I know that even multiplicities, when a root has an even multiplicity, like this one has an even multiplicity because I'm squaring it, it behaves, in this case, like a parabola. So I know that if the graph is positive here, it's going to come down, it's going to touch this root, and then it's going to go back the way it came. So it's going to be positive on this interval. And in fact, it's going to have this like parabolic behavior near the root. So I'm going to just draw that in, just like that. And when I go to the next root, 1, I notice that there's a multiplicity of 3. So I know that my graph is positive on this side of this root, and it's going to have to cross over to the negative side. But the way that it does it, we want to make sure we represent on our graph. Because it's a cubic, what happens is the graph kind of comes down, it flattens out at that root, and then it comes and it crosses the root like this, and it has this inflection point right there at the root, which is because of the multiplicity. If I had a higher odd multiplicity, like 5 or 7 or something, it would basically be more flat and more steep as you get away from the root. But I'm just representing that little inflection because of this multiplicity. And then I know that I'm going to be down here because the multiplicity is odd, so I expect to go from the positive to the negative side. And the multiplicity of this root is also odd. It has a multiplicity of 1. So I expect to come up from here and go straight through. No inflection, no curving. It just kind of goes straight through, just like a line would. And a line has a multiplicity of 1, a linear equation. So I know that my graph is negative on this interval, and then it's going to be positive on this interval. And I learned that first by plugging in one value for x and getting the y-intercept, and then thinking about the behavior near the roots that has to do with the multiplicity. And that's what this bullet is about. We want to include an accurate sketch of the behavior near the roots. Parabolic, cubic, linear. Okay? And now all I got to do is draw this smooth curve in order to connect these bits that I've already drawn. I'm gonna come down like this, and then I'll go up here and then come back down and connect to this part of the graph, and then connect this, and then go extending in that direction. Put arrows on the ends of my graph to indicate that they go on and on in these directions forever. Okay, go back and label this, the y-intercept. I just label it after I draw the curve. It's a little easier to draw the curve without having to aim for some arbitrary point that I drew. That's going to be y equal to 36. And now I'm just going to go through my checklist. Roots labeled with their x-coordinates. Yep. Y-intercept labeled with its y-coordinate. Yep. Smooth curve through all important points and on the correct side of the axis. Nice smooth curve. I already checked that I'm on the right side of the axis for each of these. An accurate sketch of the behavior near the roots. We took care of that. And finally, a note describing the end behavior using appropriate notation. So let me just think about what happens as x goes to positive infinity. This graph also goes to positive infinity. So I'll record that here as x goes to or approaches infinity, comma. Name of my function is f of x. So I will say that f of x also approaches positive infinity. That's one end of my graph, the positive end. And if I go to x, as x approaches negative infinity, my graph also approaches positive infinity. It's going up in this direction. So I'll make a statement as x goes to negative infinity, f of x goes to positive infinity. And that is a note describing the end behavior using the appropriate notation, right? As x approaches infinity, f of x approaches infinity.